In our previous investigation, we were looking at the connection between the graphs of our quadratic functions and their equations when they were written in factored form and standard form. And we saw the connection that when it was written in factored form, we could take each factor and set them equal to 0, so we could find the x-coordinate for the x-intercepts, because we know x-intercepts always have an output of 0. That's why we took each factor and set them equal to 0 in the first place. Well, once we know where the x-intercepts are, we can start figuring out the rest of our graph from there, because we know the vertex, the turning point of our parabola, is always in between the x values of the x-intercepts, and we could use that then to find that turning point. We then can get some other values to help shape our quadratic. So let's try this one here. We've got f of x equals 2 times the quantity x plus 1 times the quantity x plus 3. This equation is written in what format? It's always the first thing you want to ask yourself. And here we can see that this is already written in factored form. That's good news for us because we can take each factor, set it equal to 0, and figure out what x values we need for our x-intercepts. So in doing so, again, we're undoing each of these two equations. X equals -1 and x equals -3. So we know the values for the x, for the coordinates of the x-intercepts, and we can put them on the graph. We can also put them in our table. Now, the vertex should be in between the values of -3 and -1. Well, what's in between -3 and -1? That would be -2. So we now have the x value for the vertex. Well, how can we find the y value? What we're going to do is take the value for x and substitute it into x in our function above. Evaluate it to see what we get out. So we're going to do a -2 plus 1, see what we get, -2 plus 3, see what we get, and multiply each of those items together. So we have a total output of -2 for the function. So we know what the output is for that value for the vertex. We can put that in the table. We can also plot it on our graph. Now, we do like having at least 5 good data points to do the shape of our quadratic function. Again, that shape is referred to as a parabola. So what could we do? Well, I would suggest picking values to the left of the one x-intercept and to the right of the other. If there was a little bit more space between the vertex and the x-intercepts, by all means, pick a value in between there so you can see what's happening. But for us, since they're pretty in line, I would pick a number to the left of -3 and a number to the right of -1, substitute them into my function and see what I get out. So I'll put 0 into the function, see what I get. I'll put -4 into the function and see what I get. By evaluating each of those x values, I can see I have an output of 6. So I can add that to my graph, and now I have more points to help get the shape of my parabola. Also, if you notice, one of those points ends up being our y-intercept because it's touching our x-axis at 0, 6. Also in the table, remember y-intercepts have inputs of 0, and so we could identify it that way as well. So we've got a y-intercept here. Now we just need to connect the data points because parabolas are continuous functions, and we have our shape ready to go. Now, what else could we answer? Well, we know the axis symmetry goes through the vertex, and the vertex is at -2, 2. So the axis symmetry is going to get drawn through that point. It's a vertical line, and so our equation is going to be x equals -2. Concavity is talking about the direction the parabola opens. We can see that it's opening up. Why is it opening it up? It goes back to the equation's a value. Remember we said when a was positive, which is 2 here, it should be concave up. If it was negative, it would be concave down. So we have a concave up parabola. Domain is talking about the set of all x's for our function, and we can see we could take any value for x and substitute it in and get an output, so there's no restrictions there. So we've got our -infinity, +infinity. Range, talking about the set of outputs being used. So the lowest output to the highest output. Our lowest output here is -2, and it's being used. We're going to have our bracket -2, and the highest it's going to go, we can see it's not going to stop, so we have +infinity. And that is a successful graph of your quadratic function written in factor form. and we know all the key features about it: the vertex, the x and y intercepts, axis symmetry, concavity, domain, and range. Let's take a look at another function. Here we've got f of x equals x squared minus 12x plus 35. First thing you want to ask yourself, what form is the equation written in, or the function is written in? And here we can see that it is in standard form. Now, we know how to graph things in factored form. So the question is, can we take this polynomial of x squared minus 12x plus 35 and factor it? And we know that we can because we're expert factors at this point. Again, you look for a greatest common factor first. If that doesn't exist, you can go into your product sum method. So right now, the greatest common factor would just be 1. So we're going to skip that step, and then we're going to go to that product sum. So what two numbers would you multiply together to get 35 and add to get negative 12? Well, we could use a negative 7 and a negative 5. So now we have it in factored form. Again, we like having it in factored form because we can determine the x values for the x-intercepts to get our graph going. We take each factor and set them equal to 0 to find those values. So we're going to take x minus 7 and set it equal to 0, and x minus 5, set it equal to 0. We undo each of these equations. Well, since they're both subtraction, to undo that, you have addition. And so we have x equals 7 and 5. So I know the locations of my x-intercepts, and I can plot them on my graph and put them in my table. So this is our basic building blocks for our parabola. Now, we know the vertex has to be in between the two x-intercepts. So what number's between 5 and 7? That would be 6. So we have the x value for the vertex. What y value goes with it, though? That's the question. Well, if we take 6 and substitute it into our original function, we have 6 squared, and then we have a negative 12 times 6, and we have a 35. When we evaluate that function, we're going to have an output of negative 1. So now we know the location of our vertex. We still need at least a couple more data points to help get the right curve for our parabola going. So since one x-intercept is at 5, 0, I want to pick at least an x value to the left of 5. And the other x-intercept was at 7, 0. I want to pick an x-intercept to the right of 7. So maybe you want to use a 4 and an 8. Maybe you want to use a 3 and a 9. It's up to you what values you're using. Just make sure you've got to the left and to the right of your given x-intercepts. Just like we did for the vertex, take those values of x and put them into the function and see what you get out. So I chose a 4 and an 8. By doing so, I found out that the outputs were both 3. If you decided to go with the 3 and a 9, their outputs are 8. So we definitely have a good set of data points to create the curve of our parabola, and we can draw that in. Typically, we look for a y-intercept now. I know I'm going to have one. I can see that eventually it's going to happen. I just cannot see it in the window here that I have for my graph or my table right now. So I'm going to hold off on the y-intercept, but what else can I see in my graph? Well, if I know where the vertex is, I can tell where the axis of symmetry would go because it's going to be drawn through that vertex. So we've got a vertical line. So we've got the equation of x equals 6. I also know the concavity of my graph. You can see that it's opening upward. Why again? It goes back to the a value, and that was 1. Again, that greatest common factor. So we know it's concave up. When we talk about domain, we're saying the set of all the inputs we can use, the x's, and there's no restrictions on what we could put into this function. So we've got negative infinity to positive infinity. The range, again, the lowest output value to the highest output value. So for us, our lowest output value here is at negative 1, and there are no restrictions on the highest because we can see it's going to continue increasing. So we've got our range being from negative 1 to positive infinity. Last thing, y-intercept. Well, we know it's got to cross the y-axis. That's when the value for the input is 0. X is 0. So I put 0 in for x into my function. What do I get out? Well, I put 0 in I'll have a 0 for the first term. I'll have a 0 for the second term. I've got 35 left over. My y-intercept is at 0, 35. So now we have all the key features known for our quadratic function. Let's have you try one more. Here we have f of x equals negative 2x squared minus 12x minus 10. Again, you always ask yourself, what format is this function written in? This function is written in standard form. We know how to graph functions that are written in factored form. So can we factor this polynomial expression to get it into factored form? Let's give you a minute to do that, and then we'll check. So again, there is a greatest common factor of negative 2 we can divide out, and so we're going to focus in on the polynomial of x squared plus 6x plus 5. And we're going to think about what two numbers we can multiply together to get 5, but add to get 6, and we know we could use a 5 and a 1. So we have our factored form now as negative 2 times the quantity x plus 5 times the quantity x plus 1. Again, factored form is nice for us because we can take each factor and set them equal to 0 to have the x value of our x-intercepts. Both of these equations happen to be addition, so to undo addition, it's subtraction. That gives us values of x to being negative 5 and negative 1. And so we now have our coordinates for our x-intercepts. X-intercepts always have an output of 0, and again, that's why we're taking the factors and setting them equal to 0. The vertex has to be in between these two values. So if you're thinking on the number line from negative 1 to negative 5, what value is in the middle of those? Well, that would be negative 3. So we have this input of negative 3. The question is what output corresponds to it. Well, if we take negative 3 and substitute it into our function, whether you do it in standard form or factored form, you'll still get the same result. We should have an output of 8. So now we know where the vertex is for our parabola. We should pick a couple other input values to help get the curve, because we said we want at least 5 points. We can always do more. And in this case, we might want to do a few more because notice that there are some inputs in between negative 1 and negative 3, and we might want to know what's happening, let's say at negative 2 for an input, and we have some space between negative 3 and negative 5, so maybe we want to see what's happening with our input of negative 4. Definitely want to see what's happening past our x-intercept, so something past to the left of negative 5, so maybe negative 6, negative 7, and then something past negative 1, so maybe 0, 1 for an input. So what's nice about this is you are in charge of picking the input values to test to see what outputs correspond to them. So these might be some input values that you're thinking about choosing. Negative 6, negative 4, negative 2, 0, 1. It's up to you. I would say you need at least 2 input values besides the 3 that we had with the negative 5, negative 3, negative 1 to get a good example of what this function looks like. So I'll give you a minute based on the 2 that you're selecting, substitute the input values to the function, and see what outputs result. Here are the corresponding outputs to the inputs in our table. And we can plot those points on our graph. And now we can clearly see the curve of the parabola taking shape. Notice one of your points happens to be your y-intercept at 0, negative 10. So we can add that to our key features list. And we know parabolas are continuous, so we can connect those data values to show how the parabola is taking shape. Well, we know where the vertex is. That means we can draw in our axis of symmetry because it's got to go through the vertex. So we've got x equals negative 3. We also know the concavity of our parabola because we can see that it's opening down. And again, why is it opening down? Because that a value here, the greatest common factor, is negative 2. Now we can talk about domain and range. So again, domain, the set of all x's that can be used, and we can see that there are no restrictions on the x's. So we can say negative infinity to positive infinity. Range, again, lowest, highest. The lowest we can go, there's no limitations because it keeps decreasing. We can see those outputs no matter if we look to the left or the right. But we do have a maximum that we can reach for the outputs, and we can't go past the value of 8. So we've got from negative infinity up to and including 8. So we've been working on our techniques of graphing quadratic functions based on an equation given to us in factored form, and even if it's in standard form, we can put it into factored form and have the parabola take shape. Now, what if I give you a graph of a quadratic function of a parabola? Could you properly identify all the key features and give me a possible equation to represent it? That's going to be our goal next. A couple of things when we get there, though. Just a quick review of vocabulary. When we talk about the vertex, again, we're talking about the turning point of the parabola where the average rate of change is switching from increasing to decreasing or decreasing to increasing, right? We've talked about labeling those increasing and decreasing intervals on your graph. It's also referred to as your lowest or highest maximum minimum point of your parabola. We've also talked about x-intercepts and y-intercepts. We know points where they cross the x-axis for the x-intercepts and the y-axis for the y-intercepts. We know x-intercepts always have an output of 0, and the y-intercepts always have an input of 0. Other terms that we keep coming back to are axis of symmetry. Remember, that's your mirror image or dividing line, so you have the same image on the left and the right, and it's always a vertical line, so it has to be written as x equals the value. And that value is also going to be the same x value in your vertex. Last but not least, concavity, the direction that your parabola is opening. So we say things are concave up or concave down. So let's see, if I give you a graph, can you properly identify each of these types of key features for your parabolas? So here's a graph of a quadratic function. Could you identify the vertex, the intercepts, axis symmetry, concavity, domain range, and give me a possible equation? First thing on the docket is finding the vertex, the turning point of our parabola. And we can see that's happening right here at 2, -1. Next, we're looking for x-intercepts, where our function's crossing the x-axis, and we can see that's happening at 1, 0, and 3, 0. How about y-intercept? We have that at 0, 3. Axis symmetry, remember it's going to go through the vertex, so x equals 2.